This lecture is about anamolous zeeman effect. Yes, as it is clear from the name, it is an extension of or some special thing that is observed with the zeeman effect. Zeeman effect was well established by the Zeeman in 1896, but within a year it has been modified. That we are discussing here. We will discuss here why we move to new effects and discovery. What is the scientific side about this anamolous Zeeman effect? And what is the significance of this for spectroscopic studies? In this lecture, first we will discuss the behavior of atoms in magnetic field, how atoms respond to this magnetic fields whenever we have the spectrum obtained from these atoms and we study the behavior studies. Actually, this all is useful to understand the atomic behavior, is useful to understand the emission spectra, the absorption spectra, the behavior of electrons in various quantum levels. We will discuss briefly the normal Zeeman effect, although we have discussed detail in the previous lecture. Then we will also discuss anamolous Zeeman effect, principle of this effect, region of origin of this effect, and finally application. With the end of this section, we will be able to understand significance of anamolous Zeeman effect and their implications. We should begin by the basic word Zeeman effect. What is Zeeman effect? Zeeman effect is the splitting of spectral lines by a magnetic field. Yes, this effect is a very interesting effect. Whenever we are having spectral lines, we are studying the spectrum and apply a magnetic field, then the line will split. And the splitting of spectral lines is called Zeeman effect. Peter Zeeman was born in Zomer, a small town near Netherlands, and was a student of physics. He studied this in MagLab electromagnetic resonance group. And he has discovered this in something about 1896. He noticed that whenever we keep study spectrum in presence of powerful magnetic current, this widen the convergence of sodium under intense light. Before learning the Zeeman effect, yes, we must know the spectroscopy. A spectroscopy that is where we study spectroscope, which is an instrument that allows scientists to determine chemical makeup of a visible source of light. Here we can study wide range of wavelengths, not only optical wavelengths but also wavelengths from gamma ray, X-ray to infrared, microwaves, radio waves. When Zeeman measured the splitting of spectral lines by strong magnetic field, at that time he didn't realize the lines were splitting, but instead believed that they simply become broader when a strong magnetic field was applied near the light source, which is the spectral lines were observed. So initially he thought that this become broader. He also observed polarization effect that indicated that the line was split in a manner consistent with electron theory of Lorentz, which posited that in matter there are charged particles, electrons, that conduct electric current and whose oscillations, but he didn't realize this later on. He decided to continue the discovery and under closer inspection found that the spectral lines separated into either doublets or triplets when strong magnetic fields were placed. This effect is due to distortion of electron orbits. We have discussed this detail in the last class. In presence of magnetic field, the electron orbits distorted. And as a matter of fact, this distortion gives you generation of splitting of spectral lines. It can be asked why spectral lines split. Each spin direction has a different energy. We believe that electron has spin and two types of spin, plus half and minus half. Due to this, a spectral line split into two. Spectral doublets are now understood as due to electron spin. The electron has an intrinsic magnetic field that interact with orbital magnetic field. Yes, this Zeeman effect established a very important factor for us. existence of increasing magnetic field. As we studied, the electron can move in orbital paths, and in those orbits it also spins. Now electron has two motion, spin as well as orbital, and both interact each other. In presence of magnetic field, two possibilities are there, maybe plus or minus. That is why we are getting doublets. However, the anamolous Zeeman effect is little bit different. The anamolous Zeeman effect is about splitting of spectral lines of an emission or absorption spectrum into three or more components when placed in magnetic field. Yes, it is very interesting to note that on one side, initially we talked about splitting in two, and this is due to plus and minus. Now we are saying splitting in three. That is an extension of what Zeeman did. However, anomalous Zeeman effect was given by Thomas Preston. It is very interesting to note that why something analyzed by Zeeman and not by why Zeeman said only doublets and others said triplets and others. That is interesting. We will discuss this in the later on. Actually, Thomas Preston decided to conduct the exact experiment which Zeeman had done. Preston decided to conduct the exact experiment which Zeeman conducted in 1896. So just after 1 year, in order to determine the accuracy of the theory. Interestingly, the equipments that spectroscope that Preston had was much improved than Zeeman. He used strong magnetic electromagnets than other. And this is the reason the quality of the instrument or the quality of the results was better than Zeeman. Actually, he had good access to all universities, so he had good instruments for this. After this, he presented his experimental results in 1897, just a year after discovery, and stating that he had indeed observed the triplet nature of splitting as reported by Zeeman. However, due to his high quality apparatus, he had also reported that he had observed four-fold and six-fold splitting with a good quality photographs. That is the achievement by this. And achievement by just by taking the experiment with the same different experiment with the different instrument of high quality that is generated. Next one. As we have discussed that the zeeman effect was discovered by Thomas Peterson in 1897. This is possible with non-zero spin. Yes, non-zero spin. In the previous case, in the case of zeeman, which is possible with zero spin. So this type of spec can be observed with atoms with odd number of electrons, where we know this J is equal to L plus S. L is the orbital quantum number, S is the spin quantum number, and yes, we know this that all the observation cannot be explained with only with L or S. So we need total quantum number J. Now how this J can be obtained, that is called coupling of L and S. In LS coupling, the spin orbit interaction couples the spin and orbital angular momentum to give a total angular momentum. And total angular momentum is J is equal to L plus S. In normal Zeeman effect, we studied the splitting of spectral lines into three components in one electron atom in the presence of weak magnetic field. The electron did not have any spin in that case. Spin is 0. So that is very important for normal Zeeman effect observation. Actually, normal Zeeman effect is observed in multi-electron atoms with even number of optically active electrons. The electronic transitions occurring between singlet states where total spin is 0 with multiplicity 2s plus 1. We know that value of capital S is half, so 2s is equal to 2. So this is possible only with 1p and 1s states. The Zeeman effect can be observed with spin 0 at these states. On the other hand, when we talk about anamolous Zeeman effect, we must take care of other transitions. Other transition occurs in single or multi-electron atoms between other states. Yes, we are saying when spin is not 0, when the total spin is half. If the total spin is half, so using the multiplicity, you are having 2s plus 1, that is 2 doublet, and when you are having s is equal to 1, then the multiplicity will be 3. Now in these cases, here I am talking about 2p3 by 2 or 2s1 by 2. We observe many more lines as the effect is called anamolous effect. This effect is more general than the zeeman. Zeeman restrict only with spin 0, but it can't. It can be explained through LS coupling of the individual angular momentum vector and behavior of the resultant total momentum vector. The total magnetic dipole moment in the presence of external magnetic field. Now the total magnetic moment, we use it the word mu in place of mu s and mu l. The magnetic moment due to orbital moment is mu l and due to spin is mu s. Now these two mu l and mu s are not collinear to the total angular moment J L plus S. The reason for non-linearity is gyromagnetic ratio. The value of gyromagnetic ratio is not equal to 1. And due to this, we can observe the mu L and L that we have shown in the next slide. But here we have shown the transitions D1 and D2 lines, how transition takes place in such cases. The Zeeman effect, anomalous part, can be explained using vector model. In this model, the atom obeys LS coupling. Yes, L and plus S will give you J. In this case, the individual orbit and spin angular momentum precesses very fast about their respective L and S resultants. All are precessing. We have shown here 3 circles and everything is moving. The deep blue color S, you can see here, this one, yes. This is deep blue color S, and we also have J. Yes, J we have shown in red color. That is J. And one is left, that is L. That is we have shown in brownish yellow color. The magnetic field we use in terms of pink. Now we are showing here. We are showing here the L and S orbit, individual orbits and spin angular momentum precesses about L and S. In turn, this precesses a little less faster around J, which also precesses still less faster around the external magnetic field B. So everything is moving. First L and S are moving, then J is moving, S is moving. This is vector atom model, as various values are possible. If we apply the vector atomic model as has been done in here, we observe that the brownish yellow and SD blue vectors precess about J, which are parallel to z-axis. You can see what we have discussed in the last slide. In an applied field B, the J precess about B with a frequency. That frequency is called Larmor frequency. You are observing B is a purple, is a magnetic field, where red is the J. Now just go downward directions, which is center, what is missing. Here you can observe that L and S are precessing about J. You can observe this. L and S are precessing, and L and S precess more rapidly about J. Can you watch this? The speed is fast for the lower two circles due to spin orbit interaction. Spin orbit effects therefore stronger here. And finally, we observe less pressure, that will Larmor frequency there in the top side. Due to precision of this angular momentum vector L and S about J, the magnetic moment vector mu L and mu S as well as mu precess about J. Only the component of mu parallel to J. Mu J survive as all the components of perpendicular to mu is 0. Only mu parallel to J will survive. In this way, the splitting of labels depends only on mu J, which is anti-parallel to J, and like J, presses slowly around the external magnetic field B. The corresponding potential energy of interaction we can calculate, and is given by, shown in the next slide, del E. Del E is the interaction energy, which we use as mu J dot P. In place of mu J, we can use the word E upon 2m G into J, where G is called G factor, Landé G factor, into B. Or J dot P can be written as Z component of J B or MJHB. This G factor is generally can be written as 1 plus J into J plus 1 minus L into L plus 1 minus S into S plus 1 upon 2J J plus 1. Thus, energy level splits into 2J plus 1 from minus J to plus J, which is the region of getting many lines. In this case, we should note that the singlet states of spin quantum numbers is equal to 0, so that J is equal to L, as we have discussed in the old law. The G factor become equal to gyromagnetic ratio 2, and hence the above formulation reduces to zeeman, normal zeeman effect. So when H is equal to 0, the same formula, the same equations can give you zeeman effect, normal zeeman effect, which was explained earlier in terms of only orbital angular momentum. without any spin, only with angular momentum and magnetic moment. But the origin of anomalous effect gave you a new dimension of spin. The emission spectrum of the atom placed in external magnetic field B will show additional linear lines apart from origin lines, which correspond to situation when B is equal to 0. The pertinent selection rule for electric dipole transitions are del S will be 0, del L will be 0, plus minus 1 and so on, and so the del J will be 0, plus minus 1. The spectra can be understood by applying the selection rule for J and Mj here for D1 and D2 lines. Del J can be taken as 0 or plus minus 1, and Mj can be taken as 0 or plus minus 1. Using this, we can calculate the value here, various spectral lines. When the del J will be 0, when the del J will be 1, we know this, that can be written as L plus S, so can be calculated. And using this, you can explain this behavior of anomalous zeeman. If we study the polarization of the transitions, then they follow the same pattern as zeeman, the normal zeeman effect. For example, if we consider D lines of right produce 3p2ts transitions, that it gives the same behavior. So, in this lecture, we have studied anamolous zeeman effect, how it is different than normal zeeman effect. We have also studied how we got this anomalous zeeman effect. This has significant in the way that it includes all whatever we have discussed in zeeman. It gives additional behavior, and yes, in the same year or within 1 year, they have given both the laws, from where we can conclude that the results given by the anomalous is more resolved with a more resolution than the first one. And that is why he got more lines, and this leads to a development of quantum spin concept of intrinsic spin. That is why it has very significant value for us for studying spectroscopic studies. Thank you. Take care.